Lesson 10 is on VSEPR models of covalent molecules. So VSEPR, what is it? We're also going to go into molecular geometry with the axe method, and we're also going to talk about bond lengths and strengths. So VSEPR, or valence shell electron pair repulsion model, is a idea that valence electrons are placed as far away from each other to minimize the repulsion forces between themselves. Two negatives don't attract, they repel. So that's why it's called valence shell electron pair repulsion.
When we look at our models that we see here, we've been drawing the methane, for example, which we've done. We've been drawing them as very flat structures, but in reality, because these things are in a 3D space, they actually take up their own angles and distances. And using the VSEPR model, we can get different shapes that these covalent molecules actually resemble in real life. So we're going to talk about what we call the axe method, AXE. And you're noticing after the A, the X, and E, we have parentheses, and that's where a very particular number goes. In class, we've given out a reference sheet for the axe method, but it's very simple to do. When you look at a chemical formula, the number of center atoms, dominantly it's the first one, or it's the most unique one, that's going to be A. You're going to put a number in there. It could be 1, 2, 3, 4. X is going to be the number of terminal atoms. So if we think of H2O, O is your center atom, and there are 2 terminal atoms, so X would be 2. And in a situation where you have any lone pairs, that's using your drawings to figure that out, you're going to put the number after the E. We're going to show you what this all means right now. So of our first type of VSEPR model, we're going to talk about linear. Linear means that the model itself is 180 degrees, which means it is a perfectly straight or linear line. Our first of the axe method is an AX2, which means you have 1 center atom with 2 terminal atoms. Your center atom, however, contains no lone pairs. Or it could be AX. That means you have 1 center atom and 1 terminal atom, and because it's just the 2, you're always going to have a straight 180 degree linear model.
The second model is bent. This is where we have 2 lone pairs that cause a repulsion that causes the shape to be bent in shape. So you'll notice for like H2O, there is 1 center atom, so 1A, 2 terminal atoms, so X2, and there's 2 lone pairs around the oxygen after you draw out its Lewis dot diagram, so there's E2.
There's another shape that we call as trigonal planar, which is always going to contain 1 center atom and 3 other terminal atoms that go around it. Now these guys are going to be flat. That means if they're lying on a table, none of them would be above the other. They would all be on the same plane.
Another one is trigonal pyramidal. So NH3 does this, so does PF3. There's 1 center atom, 3 terminal atoms, and 1 lone pair that pushes them down. So instead of them being flat like the one before, they have more of a pyramid shape to it.
You can kind of think of these guys almost as those massagers that have like 3 little heads that would massage your back.
Oh, yeah. Glorious things.
And we also have our last one, which is called a tetrahedral shape, which is commonly found in a lot of organic molecules since carbon can always make 4 bonds. So here we have 1 center atom with 4 terminal atoms, giving you a tetrahedral shape. This means that you have 2 atoms that are on the same plane, but then you have 2 other atoms that are either closer to you and 1 that is further away from you, thus giving you a 3D shape.
So bond length, if you look at the picture right here, you'll see that a single bond is further away from each other than a triple bond. So as you increase the number of bonding in between two atoms, you'll decrease the length between them.
Endothermic reactions, which is breaking bonds, putting energy into breaking a bond. This also tells us that since triple bonds are so close together, it's going to take a ton of energy to break a triple bond apart. So a single bond would require the least amount of energy, while a double and triple require more.